Okay. So, good morning, everyone. I hope you had a good dinner last night and that you slept well, because it's going to start by some disorientation. So if you didn't take a good rest, then it would not be good for you. So today we are starting with Krijn.
Yeah.
And he's going to talk about the disorientation faults in CSIDH. So Krijn is a PhD student in post-quantum cryptography at Radboud. Okay, thank you. So Krijn, you have the floor.
Thanks. So yeah, the title is Disorientation Faults in CSIDH. It's maybe a bit more of a lighthearted talk because we have no genus 2 anywhere in the talk. And it's joint work with Gustavo Wanogos, Juliana Kremer, Tanja Lange, Michael Meyer, Lorenz Pani, Jana Satakova, and Monika Trimoska, which means that if you look around, you'll probably find at least 3 or 4 of them. And before we start, I actually want to tell you about the pub crawl we did yesterday in Leuven to celebrate our paper. So we started out at the KU Leuven, and then the plan was we go to the Giraffe, have some shots there, and then maybe we go to het archief, and then we end up in the block hut. And it was quite fun, but there's a problem with a pub crawl that you drink a lot of alcohol, and you may get a bit confused. And then, for example, Lawrence ended up at Vakbare Elixir, and after a while, the Jana and Monica were actually dancing in the Ambiorix while we should have been at the block hut. And also our Germans from Regensburg ended up in a totally different place called the Blauwe Kater. And I ended up in some weird club somewhere that kept sending me tweets to sign up. And actually only Tanja and Gustavo ended up in the block hut, which was a bit of a piety to celebrate our paper. So what we decided to do was to first in each other's pubs to look for each other, so that we're at least a bit connected, and then just go out on the streets, walk around randomly to try to find each other. And this worked out quite well. Jana managed to find Lawrence quite quickly. And then a bit later, we also all managed to connect up with Tanja and Gustavo in the block hut. And then we could spend all our efforts to try and find our Germans. And then it took a bit more time, but we managed to find a connection there. And then we were all connected and we could celebrate our paper at last in the block hut. And why am I telling you this? Well, if you now replace bars with subgraphs and street with isogenies and drunkenness with fault injections, then you basically have the paper that we've written. So let's go from disorientation attacks to this key recovery on CSIDH. And to do that, I will tell you about 3 things. First, about the class group action evaluation. And probably you know the class group action evaluation pretty well in CSIDH, but I need to go over it once more to sort of get you aligned with our way of thinking about it for this paper. And then we can move into how we can do a fault injection to break CSIDH. And if we've discovered that, then we'll move on to try to break CTIDH. So let's start with the class group action evaluation. So we all sort of know that you have this isogeny graph, and we're taking the isogeny graph over FP, and we take a starting curve E and some element of the ideal class group. And in CSIDH, you take this by taking the right powers EI of the generators LI. And then what we want to compute is this other curve that's somewhere else in the graph with this path E prime. And then if we do this very practically in CSIDH, we take a prime of this form, 4 times all of these LIs, and then say your A can be generated by these coefficients. So the 3 would be E1, the 1 is E2, of course, etc. And then essentially what we do is we get a random FP point and we perform LI isogenies if we need to perform them. And then we push P through until it's sort of empty, until we can't use it to perform these isogenies anymore. So let's look at the example where we're just having positive coefficients right now, and that we imagine sort of magically that every time we pick a random point, it is actually a full order. Then how we perform this key? Well, we would first get this point over here, and then we would use it to perform an L1 isogeny, and you push P through. Then an L2, push it through, L3, L4. Well, we don't have to do an L5, right? It's not in the key. L6 and then L7. And then at this point, P is sort of empty because it can only have, well, these factors once. because of the prime that we chose. So we need to refuel here. We get a new point P, and then we use it again, push it through until we've performed these 1, 3, 4, and 7s. And here it's like empty again for what is left to perform, right? We could use it to perform a 5 or a 6 isogeny, but then we mess up our key. So here we refuel again, perform the L1 and L4, and refuel again a last time to get to E prime. And now we're at E prime, and then we're happy. And if you look at it like this, we performed these allies with the first point, these ones with a second, and with the third only 2, and then we had to use a fourth point for this last coefficient. And that means that we performed the Li with EI larger than or equal to 1 with the first point, larger than or equal to 2 with the second point, and so on. Now, if we could go to a bit of a larger example, like a proper CSIDH 512, we would of course have 74 small odd primes instead of the 7 we just had. And the coefficients, we sample them from -5 to 5. So we also have to do negatively oriented isogenies. So we act with Li inverse when EI is smaller than 0. And then if you look at it in the same way, what's the first positive point doing? Well, it's doing all Li such that EI is larger than 1. And then with the first negative point would do all Li such that EI is smaller than or equal to -1. And so on and so on. And if you would just have full order points, you need 5 positive points and 5 negative points. Well, you don't always get full order points, right? You miss a specific torsion for Li with a probability of 1 over Li. And for a large Li, that's not really a big problem. But for example, for 3, well, 1 in 3 points won't have the 3 torsion. So in reality, we use the kth positive point to perform these Li that we just mentioned, except if we have missing torsion here. If our point P cannot perform them, well, we cannot perform them. And then that's actually not the whole picture, because this messes things up a bit more. For example, if the first positive point was missing the torsion, the 7 torsion, but we wanted to perform a 7 isogeny, the second positive point in this run will need to perform this 7 isogeny still. So actually, you sort of get an effect where the missing torsion from previous points pushes forwards through other points, and then the complete set that you're performing is the Li with EI larger than or equal to K, except for the ones that you're missing, but you might make up for previous rounds. And that's what we call torsion noise. Now, that was good enough. So let's go to fault injections. I'm not sure if the people here are actually a fan of fault injections, because they sound a bit overpowered. It's essentially how we can skip an instruction and mess up your cryptographic algorithm, which is it's a bit strong, but actually the results that we get are pretty fun. So you can still enjoy the talk, even if you don't like fault injections. And what are we going to inject? Well, this point where we refueled for a new point. So every time we refueled at some curve, we got a new point, and we check if it's on E itself or on its dual. And if it's on E, we can use it to perform these positive Li's. So we call this point positive. And if it's on a dual, we say that it's a negative point, because we can use it to perform the negative Li's. And we in CSIDH, we capture this just with one value S. We set S to 1 if it's positive and S to -1 if it's negative. And then what you can do is when you're getting a random point P, in a normal computation, okay, you get a random point P, and then you compute, it's on E, so I set S to 1. And what we fault inject is exactly this computation, so that now the computer says, P is actually on the dual, so I will set S to -1. But it isn't. P is actually on E. It's just the computer is now messed up. So what will the computer do? It will use P to perform all positive Li's in the normal computation, but in the fault injected computation, it's actually performing the negative Li's. But these negative Li's, it's actually performing them in the positive direction, because the point is actually still a positive point. And then after performing this, he updates the parameter. So in both cases, this goes correctly in some sense, right? If EI was -4, it will now go to -3. But it did this Li in the wrong direction. So what do I mean by that? If we would have had this situation, we get a positive point, we perform L1 and L2. Then here we get a negative point, and we perform L3 and L4. In a fault injection situation, imagine we got a positive point over here, we perform L1 and L2. And then here, this is a very confusing part. Here we would have gotten a positive point. Here we get a positive point, assume, but we fault it and we make the computer think it's a negative point. Then it starts to perform these coefficients, but it performs them in the wrong direction. So you end up at a different curve. You end up at ET. It's what we call a faulty curve. And then it starts to get interesting if you look at what is then actually like the difference between a faulty curve and the curve we were supposed to end up with, E prime. Well, we applied L3 and L4 instead of L3 and L4 in the inverse. So E prime differs from ET by the square of this, right? L3 squared, L4 squared. So they're separated by a isogeny of degree Li squared, where the Li are taken over the coefficients that are less than or equal to -1. And this is very reminiscent of what we just had, right? We said, well, the first positive point performs the Li such that these EI are larger than or equal to 1. And the first negative point smaller than or equal to -1, and so on. And you can see that if we inject the right point, it will start to differ by exactly this set, but squared. So what I mean by that, if the first point is negative and we flip it to think it's positive, well, actually the point still stays negative. I will just abuse the notation here and say that we flipped it to positive, but it's only the orientation we assign to the point. But then we end up at this faulty curve that is Li squared away from the E prime. And this one we call E1 plus. Why? Because it's, well, we injected the first point and we flipped it to positive. If you would have injected the fourth point and flipped it to negative, you would get E4 minus, which is all of these EIs away from E prime. And this starts to get, starts to reveal information about our key, right? If we have a faulty curve E1 plus, and we actually have the public key E prime, and we find the isogeny in between, then we would recover all of the coefficients EI larger than or equal to 1. Okay, this is approximately 33 of them will be larger than or equal to 1. And that's quite a lot of isogenies that you would need to compute with like a meet in the middle approach to solve. So this is not yet going to work. So we can do something better. Let's say we hope that we find all of these curves. We do a number of computation. We repeat the same computation a number of times, right? We keep on applying our private key A to E, and then we inject these different computations once in different rounds. And then we hope that we end up with like E1 plus, E2 plus, et cetera, et cetera. Because now these are connected in this way, right? If E1 plus was connected to E prime by all EI that are larger than or equal to 1, and E2 plus is connected by all EI larger than or equal to 2, then their difference must be those EI that are exactly equal to 1, and so on for all of the other ones. And actually these gaps shouldn't be so big. They should be approximately, this is the general plan actually that we're going to do. So the goal is we were trying to find all of these EI plus and EI minus, and then we connect all of them, and then we recover the secret key. This works much better because this approximate gap here is like 6 or 7. And so with a meet in the middle, this is actually quite feasible to the power 29. And then you can also say like, with the pigeonhole principle, you have one gap that's at least 6. So you can recover that one quite easily, and so on and so on. But it actually gets a bit better than this, because right now we're still assuming that we always would get sort of full order points, and this was too magical to happen. So it will quite often happen. 18% chance actually that you get a full order point. So in most cases, you do not get a full order point. You get a lot of these missing torsions. So you would end up at a faulty sample, faulty curve, that is not really E1 plus, because it may have missed, for example, the L1 torsion. But it's very close to E1 plus. If you would have done this run 5 times, and you find E1 plus in this faulty curve, this small isogeny is very easy to find because it's only separated by a degree Li squared isogeny. which is almost trivial to find. So if you would have taken, let's say, let's say 10 samples where you flipped the positive first point, it would look something like this. You get probably like 6 or 7 faulty curves because some of them will overlap. And then what's the most probable curve to be appearing in this set? It is actually E1 plus. That's the highest probability of appearing, simply because a point is more likely to have certain torsion than to not have it. So makes more sense. And then we use a magic tool from Lawrence, which we call pop crawl, to start crawling around these public keys. And it will find this isogeny, for example, and then maybe these ones as well. And then it connects these other ones as well. But this is actually quite nice because all of these Li that are appearing in this sort of graph are Li's that have EI larger than or equal to 1. Because otherwise they wouldn't be appearing here. We're just using a positive point, flipping a positive point. If it's missing torsion, then this will appear here. But if it's sometimes not missing the torsion, it means that it was performed, and so that EI was larger than 1. So we actually, this missing torsion is actually kind of nice because it gives us a lot of information on the orientation of these EIs. So then you would maybe say, okay, we start with a lot of samples and just from different rounds. And let's see what happens if we try to do this for all of these graphs over here. So you could think quite long about, we have these number of samples and then we need to pick this and this and this. But actually, if you just run pop crawl, it's much faster. It just starts connecting all of these samples to the graphs by itself. And it takes like, I think, 10 minutes or so to do something like this. And then you get a picture sort of like this. Actually, this is what we expected to happen. And then we ran this and we had quite a nice analysis. But it turns out you also get a curve like this. And that was quite confusing for the first hour that we looked at it. We couldn't really explain what's happening over here. But actually, this is also because we skipped over a phenomenon that I just mentioned. We had this torsion noise. If you had, like, for example, E17, if it's equal to 2, but you had a run where in one of the first 2 points, it wasn't actually performed, and you then flip a negative point to a positive that does have the torsion for L17, then it will perform it only in the 3rd round, and it might just end up over here if the rest of the points are also performed. And then it sort of appears above this sort of brute. But this is also quite nice as well, because this can actually only happen if E17 is equal to 2, right? If it was equal to 3, we would expect it to turn up in E3+. If it was equal to 4, it would be somewhere there. If it was equal to 1, it could happen, but it's very unlikely, right? Then you would need the first point not to have it, and then the second point also not to have it, and third one. So actually what you can conclude from this is if you see this happening, then this degree is also, you actually know a precise value of this EI. So distortion noise gives us info on the value of the EI. And then together with all of this, we sort of define these graphs, these 10 graphs, subgraphs of the isogeny graph, where G1 plus is all the nodes that are connected to E1 plus, and so on. And together with all this, all that we now are left to do is actually connect all of these graphs to each other. And if we manage to do that, we can recover this isogeny, and that were the breaks that we were looking for to give us the information on the EI and on the key. And now you might see why I started out with this analogy. So these are the bars, right? And these are the people in the bar. This is Jana and this is Monica, and they managed to find each other. But now they still need to find Lawrence in this graph. And then if everybody finds each other and we connect to the block HUD, then we're happy and we recover the key. Now, with the extra information that we get from these graphs, like all of the Li that appear in this positive graph, well, we don't have to use them when we're searching for these breaks, right? We know already that these will never appear here. That gives us a lot of knowledge, which decreases the search space. And it gets even better. If you find one of these breaks here, then you know all EI that have value 1. And you don't even have to use them in this search because you already know that they're not going to appear here. They're just going to be there. So every break gives you more knowledge. So this pigeonhole principle, that one has a gap of at most 6, let's say it's this one, it helps you a lot because you can immediately decrease your subspace from 74 primes to 68 primes, essentially. Okay, now I skipped over one point, which is which point would we actually hit when we were performing this? We can see sort of, you can imagine a chip running seaside, and you can see it's now performing the first point, it's performing the second point. And let's say we hit the third point. We don't really know, is this third point the first positive point that it's performing, or is it the first negative or the second positive? So actually what I'm asking is, if we hit the nth point in a run, in which graph are we going to end up? Well, if n is 1, it's easy. It's either the first positive point or the first negative point. We don't really know it yet when we hit it, right? We just flip it and hope it flips the orientation, and we get a faulty curve. But if you get a number of samples from the first round, then you actually get these isogenies that were connecting them. And therefrom, you can reconstruct if it was, in which of the true graphs it was, if it was in the positive one or the negative one, by the directions of the arrows. And now if you hit the second point, there are essentially 4 options. Either the first point was positive and the second point was positive, but we flipped it to negative, or the first point was positive and the second point was negative, but we flipped it to positive, and the other way around for the other orientations. Now, these 2 cases where you had first a positive point and here you had a positive point, but you flipped it to negative, this is actually as if you are performing the first negative point. The computer will think, with this point, I'm going to perform all EI lesser than or equal to -1. So you would still end up in sort of this case. Only in these 2 cases are you getting the new curves. Only in these 2 cases is the computer going to perform the EI with coefficients larger than 2 or smaller than -2, and you mess up this computation and you end up in G2 plus or G2 minus. This is what we call an effective curve, right? So if we hit the computation of, we hit the run at the second point for like 10 times, we're going to have about half of them are going to be effectively curves from round 1, and half of them are going to be effectively curves from round 2. So in general, if you hit the nth point, you're going to get effective round R curves for all R smaller than or equal to n. And this depends on the signs that were before the point that you hit. And you can sort of look at it like this. Well, let's say you want to hit the rth negative point. You need to make sure that in the run up to this point, you need to have r-1 negative signs. So r-1 out of the n-1 signs needs to be negative, and this is the amount of options that you have there. But if you want to get information on around n, then you really only can get away with plus, 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 or minus, 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 minus. So in round n, if you want to get an effective round n curve, your chances are actually quite small. So you need to take more samples. So if we want to get this round 5 samples, these E5 plus or E5 minus, or curves that are close, then we need to get plus, 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 and minus, 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 which odds are 1 in 16. And that means that we need sort of like maybe 100 round 5 samples to be sort of sure that we have at least one sample. That we have at least one sample like this and one sample like this. And then we sort of have enough information to start raking it. Because if you wouldn't have one of those samples in the 5th graphs, then you sort of, your gap is too big and your computation power is going to increase a lot to solve this gap. But the nice thing is, if you just take 100 round 5 samples, actually a lot of them are going to turn out to be round 1 to 4 samples as well. Just because of this, this effect here, which is nice, you get them for free. So at some point we just decided, let's try it. What happens when you take 100 round 5 samples and you send them to Lawrence so that he can fire up his insane machine to run popcrawl. And then after like 25 minutes, you get a picture sort of like this. So here, these are all these subgraphs. This one is very lonely, but nothing we can do about it. We got all these subgraphs, and here we actually see that it already sort of connected some of these subgraphs. This was after 25 minutes. Here is the public key. This was what should have happened. The colors don't really imply much, but the non-gray ones are the samples, and the gray ones are the breaks that it finds. So after like 25 minutes, it managed to find 4 breaks because we're down to 7 components, and we started with 11. We need to get down to 1. But then this would be a break that it finds, and this would also be a break that it finds. And this is probably like, if this is E primed, this is probably going to be like E5 plus or G5 plus really, G5 minus 4, 3, etc. And then after, I think 46 minutes, we were down to 6 components. Run it a bit more for almost an hour, we're down to 5 components. And the most that we could really do with brute forcing or with this meet in the middle sort of thing is getting it down to 4 components. And then you're sort of seeing that these 2 components are really far away apparently from the other ones. And this one, we didn't manage to connect it yet over here. So now we need to start thinking and applying these tricks, right? So here these are probably negatively oriented ones. So all of these negatively oriented ones, we don't need to use them in a positive search. And all of the positive ones, we don't need to use them in like a negative search. And if you start doing that, you might be able to find one of the more remaining breaks. And then here you can even do more specific analysis, right? If you have E prime over here, then this is going to be E5 minus. And what's very likely is that this one is going to connect over here, probably, or maybe over to this one. But at least here we have E5 plus, E4 plus, E3 plus, E2 plus, and E1 plus. So that one is fine. We don't have to worry about the positive side apparently anymore. Just need to connect this probably over here and maybe this one over here. And then you can start to use a very directed search and solve it. And then you reduce it all to one component. And then you get this sort of graph that's like a sea dragon. But now how do we get from, if we have connected all of the components, how do we actually get to the secret key? It's not going to work well with this picture. So I made another picture. Actually, Lawrence made another picture, I think, for a smaller example with CSIDH 103. But the idea is the same. Here we'd have E prime, and then you have E1 plus, E2 plus, E3 plus, E3 minus, E2 minus, and E1 minus. And then you can read off the coefficients just like this. So what are the coefficients with EI equal to 1? Well, it's the 19th one, the 9th one, and the 2nd one. And for EI equal to 2, 3, 18, 10, 7, and 13. And we'll give you this key. And then you've recovered the key. And that's actually, yeah, it was nice. You find it, and then you break CSIDH 512 essentially in 100 samples. So after breaking CSIDH, what's the next step you do? You try to see if you can do it for CTIDH. But for CTIDH now you're in a bit of a confusing situation because CTIDH has a very different way to perform these sort of perform the key, or how it goes through the key space essentially, because it's sort of like a bus. And what do I mean by that? Well, CSIDH is definitely not like a bus, right? We had this picture where the first positive point performed this one and the second one this, and it's actually sort of stratification of the key. And it's similar to the example I showed in the beginning where it was the graph when I had these layovers. And what CSIDH would do is actually it would group together different degrees, like E1, E2, and E3 into a bus stop here. And also for the second one, maybe it takes E4 up to E7, and then E8 up to E11. And then all of the isogenies that you still need to perform line up very neatly at the bus stop. So L1, 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 and then L2 negative, and here. Like this, always like well ordered. And then the positive and the negative point, you can think of them like a bus. And CTIDH is very nice because every round, you know that 2 buses are going to go. There's going to go a positive bus and a negative bus. And it takes along the LIs. So the positive point takes along the first positive passengers and the negative, then first negative ones. So this is what the first point performs. And you can see that, well, the second point coincidentally performs the exact same isogenies. And then the third point in this example would perform L1, L5 for the positive point and L9 for the negative point. And then you get this. And actually, so CTIDH would have, would do it for all 74 degrees, and it divides it into 14 batches or bus stops. And there's a limited amount of people that you can then fit on the bus, right? If you have 14 bus stops and you pick up 1 passenger every bus stop, then you're going to have 14 people at most on the bus. But on average, it's going to be about 7 people on the bus. And there's a maximum to the amount of people that are allowed to stand here, which is denoted by MI. So it's the amount of isogenies that you're going to perform in a given batch. The maximum for this is 18 in CSIDH 512 for these bus stops. So we need to do 18 rounds of this. And then you may have some missing torsion somewhere. So maybe you need to do 19 or 20 and sometimes 22, I think, rounds. But this is actually much nicer for our attack, because we previously had that the first positive point would be forming up to 33 isogenies. And if we flipped it, it would get very far away from E prime, and we had to do all of this analysis. But here, you can expect actually that it's going to be only 7 isogenies away. So flipping the point, or flipping a bus, changes the orientations again. But in CSIDH, we also know the bus schedule really well. It does 2 buses every round, 18 times. And you can just, it's also ordered. You can see the run and you can just say, I want to hit the 7th run, the negative point. You can just do it. Much better than this effective curve analysis that we used to do before. Here, it's always an effective curve. And you end up at a distance approximately 7 isogenies away. So it's pretty easy to just brute force or use meet in the middle for all of these faulty curves that you get directly to the public key. And you need to only flip 2 buses per round for approximately 18 rounds. So you get a total of sort of 36 samples if you would have all of them perfect, right? If you would have no missing torsion. And maybe we need to do a bit more because you have some missing torsion, but it's not so much more actually, because you can also sort of recover these faults and so on. So comparing CSIDH 512 versus CSIDH 512 in our fault injections, CSIDH 512 is using this 1-point strategy where we don't know which point we hit and we need to look for these effective curves. But CSIDH with a 2-point strategy, you can just hit it very precise in the nth round and in the orientation that you want. And then CSIDH, this distance between ER plus and E prime was too large. And so we had to go through ER plus 1 plus. This was the general plan. But here actually we will sort of see a graph sort of like this quite often, where the distance between ER plus and E prime is usually small enough that you will just be able to brute force it. We don't have a picture of it, unfortunately, because we managed to lose it. But it gets better still. Because for now we performed this attack and this also sort of works. It's not so much work, but you just need to do a lot of computations after you're getting all of these samples. And then we thought maybe we can do better here. So we were very happy that Jana at some point said, can we use the twist? And it's always nice when you're using a CSIDH paper that you can sort of use the twist. So when we did now, we attack this general E prime computation, we have control over which public key we would feed to Bob in a CSIDH or CSIDH case. If we would feed it E0, it would compute EB. But then if we feed it the twist of EB, it starts to compute E0, which means that all of these faulted curves end up very close to E0, regardless of the secret key. But if you find a break, it still leaks information on our secret key. And that means that you can just sort of take E0 and all of these, sort of the graph that's around it, and then compute all of the curves up to a certain distance D, depending on how much time and effort you have. That makes it much faster to find the breaks, especially in the case of CSIDH. Why? Because in CSIDH, you can just pre-compute every possible curve, every possible faulty curve that can appear from a faulted run. Because if you have BI batches containing NI degrees, right, there are not that many possible configurations, how do you say it? Possible number of curves that can appear. It's just a product of NI plus 1, which is 2 to the power 35.5, which is very big, large file, 250 gigabytes, but it's certainly doable. And you only have to do it once to be able to apply this attack to every key that you want to attack. And then for every sample that you would get in a faulty run, you can immediately recover E0 to ET. And from this, you can immediately recover a lot of the coefficients, EI already, or a lot of information on the coefficients. So then you just need to take 40 samples and you sort of immediately get the key. You don't have to do all of this post-processing because you did all of the pre-computation already. So to summarize, we shoot a laser at a chip and this results in this sort of graph like a sea dragon. And then by an analogy with a pub crawl, you first meet your friends inside of the pub and then you all sort of meet up outside to find each other. And then you get the secret key for CSIDH and CSIDH. Are there any questions?
Thanks, Krijn. Questions? If you don't have any question, you have to skip lunch. So ask questions, please. Yes.
How does the attack scale for larger C-side parameters?
Yeah, so you would get much larger gaps, right? Probably. It depends a bit on how you scale C-side itself. But yeah, if you go to C-side 1024, it becomes more difficult to find these gaps. And for C-side, you sort of get a tricky situation because it's not really clear how you would do the batching in larger parameters. But I think definitely for C-side, you're in a very easy situation where you would have enough computer power to recover all of the gaps. For C-side, it would depend, I think. If your gaps really get quite large, like if you have a gap of 14 somewhere, it's very hard to recover because you really need a lot of computation power. And then there are tricky things like if you have scale, in scale you only have the coefficient 1. And there actually you have a sort of natural protection, I would say, against this attack, because if you flip it, you will always just end up at the action of just once, right? So it depends a lot on how you would scale to larger parameters, but it applies, I think, the attack would still apply in almost all situations. You just need to do a bit more work.
In this last setting, so this twist one, I suppose the storage is going to explode, right?
Yeah. But you can also do sort of different tricks there where you would not compute every curve, but you just sort of compute. You can the trick still works that you can sort of pre-compute quite a lot already. So you're always shifting computations from behind to before the attack, in some sense.
And is there some trade-off here with pre-computation and to do a little bit less pre-computation and a little more post?
Yeah, that's definitely, well, yeah. So in this case, we just thought, well, for this example, you could definitely sort of do it if you would spend enough time. But yeah, you have this trade-off, of course. If you just decide to miss a few, then afterwards, and your sample is not in, you start crawling around your sample until you hit one in the pre-computed ones. There's still a very obvious question, actually, that we should answer before we go on to the next. I'm wondering if anybody comes up with a question. Otherwise, I will just ask it myself. But
okay, someone has the question.
Yeah. So, did you do any laser experiments and try to do the thing?
Yeah, we did. We had 2 guys doing laser experiments to shoot on C-side, but they sort of dropped out after a bit. So we don't really know what happened there. But they managed to shoot at the first round. That was pretty easy. But then I think they got occupied with other stuff.
But they did manage to hit exactly this one bit that you want.
Well, it's not really a bit. This is actually the question that I was hoping somebody would ask. What do we actually inject? I skipped over this completely. But what we want to do is flip this bit S, right? But we're not shooting exactly at S to flip it. What we're actually doing is there's a number of options to cause S to flip or to cause this behavior, which is when you're computing this x to the power 3 plus ax squared plus x. If you skip any instructions here, then you sort of get a random FP value of which you're computing if it's a square or not. And then in 50% of the cases, it switches the orientation. That's one thing that you can do. You can also change one in the bit of the memory in between when you start using the point and when you computed this, and this also sort of makes it into a new random point 50% of the times with a different orientation. And the third one is actually really, really weird. In some implementations, if you skip an instruction in is square, you would get a sort of weird, this is a Legendre symbol computation, right? And you skip an instruction in this exponentiation and you get a result that's not 1 or -1. And surprisingly, there are implementations that will always return -1 when the answer is not 1. For example, the original C-side, for some reason, does this. And then you would always be able to flip to a sort of negative situation.
We have time for one last question. Yes.
Did you look into countermeasures or how to?
Yes, good question. So the countermeasure is a bit tricky because we wanted to make sure that you sort of couldn't do it fault twice or something and get the same behavior. So what we thought of is if you keep track of pseudo y coordinates, so z here is x to the power 3 plus ax squared plus x, and here you compute essentially the root of Z, and you keep track of this, then you can compare it to Z. You can compute pseudo Y, and if you square it, it should be equal to Z, and it's equal to 1. If you square it, and it's equal to minus Z, ZS equal to -1. And then we reuse this over here. And also we recompute Z prime over here, which means that if you inject over here in this computation, you would need to cause exactly the same injection over here to make sure that this XQ and ZQ are actually different, the same value. Otherwise you mess up this whole point. And then if you just sort of make sure that this computation is done in different ways, like not in the same order, then it's almost practically impossible to get the same sort of fault. And you get a chance to think 1/p to cause the same fault. So then we think it's secure. This is for the 1-point strategy of CSIDH. CSIDH would use a 2-point strategy, which is sort of the alligator 2 map. But then you also need to incorporate these pseudo Y coordinates when you're computing the Legendre symbol over there, which we now named alligator, because it has greater protection than alligator.
Okay, let's down the speaker again.